Minimum supply circuit ampacity is the minimum continuous current that the branch circuit must be able to supply to the motor. It is calculated as 125% of the motor's full load current, also known as FLC. Minimum fuse size is the smallest fuse that can safely protect the motor from overcurrent. It is determined by considering the motor's FLC in the circuit protection curve. Maximum fuse size is the largest fuse that can be used without damaging the motor. It is usually set to provide some margin of error and account for potential variations in operating conditions. In this case, the motor's FLC is 2.2 amps from table 430.148. Therefore, the minimum supply circuit ampacity equals 2.2 amps times 1.25, which equals 2.75 amps. The minimum fuse size equals 30 amps, the next standard size above 2.75 amps. Your calculations are correct up to the point where you get 2.75 amps. To determine the appropriate branch circuit feeder, you need to consider the overload protection requirements for motors as per NEC section 430.32. For motors over 1/8 horsepower, overload protection must be provided by a fuse or circuit breaker rated at not more than 125% of the motor's FLC. Based on this requirement, you would need to use a circuit breaker rated for 25 amps or 30 amps. Note that you could not use a 40 amp breaker, as it exceeds the 125% limit. Therefore, the smallest branch circuit feeder you can use is 12 AWG copper wire, as per 310.16, and a 25 amp or 30 amp circuit breaker, as per 430.32. Yes, assuming the unit is rated at 75 degrees Celsius, you could use a 12-2 NMC for the branch circuit feeder and install a 25 amp or 30 amp circuit breaker to protect the motor. In more detail, let's break down how these nameplate values are determined for AC condensers, focusing on a practical example. When dealing with electrical installations, especially for residential dwelling units, understanding motor nameplate ratings is crucial for ensuring safety and efficiency. Copper prices and the desire to optimize branch circuit feeders make accurate calculations essential. Consider an AC condenser unit with the following nameplate information: 1/6 horsepower, 220 volts, 60 Hz, minimum supply circuit ampacity 25 amps, minimum fuse size 30 amps, and maximum fuse size 40 amps. The question is, how are these numbers derived, and what are the implications for selecting the appropriate wiring and circuit protection? Let's start with the basics. The horsepower rating indicates the mechanical power output of the motor. In this case, it's 1/6 horsepower. The voltage and frequency, 220 volts and 60 Hz, specify the electrical supply required for the motor to operate correctly. These values are standard for residential applications in many regions. Now, let's delve into the more complex ratings: the minimum supply circuit ampacity, minimum fuse size, and maximum fuse size. The minimum supply circuit ampacity is the minimum current carrying capacity required for the branch circuit that feeds the motor. This value ensures that the circuit can handle the motor's load without overheating or causing voltage drop issues. To calculate this, we need to refer to the National Electrical Code, specifically Table 430.148, which provides full load current values for AC single-phase motors. For a 1/6 horsepower motor operating at 230 volts, the full load current is approximately 2.2 amps. NEC section 430.22 dictates that the branch circuit conductors must have an ampacity of not less than 125% of the motor's full load current. Therefore, we multiply the full load current by 1.252.2 amps times 1.25 equals 2.75 amps. However, the nameplate states a minimum supply circuit ampacity of 25 amps, which seems significantly higher. This discrepancy arises because the AC condenser unit likely includes additional components, such as a compressor and fan motor, that contribute to the overall current draw. The manufacturer has already factored in these additional loads to determine the minimum supply circuit ampacity. The minimum fuse size is the smallest overcurrent protection device that can be used to protect the motor and branch circuit. It's essential to select a fuse or circuit breaker that can handle the motor's inrush current during startup while still providing protection against sustained overloads and short circuits. The minimum fuse size is typically determined based on the motor's full load current and the type of overcurrent protection device used. For motor circuits, time delay fuses or inverse time circuit breakers are commonly used to accommodate the motor's inrush current. These devices allow a temporary overload without tripping, but will trip quickly under sustained overload or short circuit conditions. The maximum fuse size is the largest overcurrent protection device that can be used without damaging the motor or violating code requirement. This value provides a margin of safety and accounts for potential variations in operating conditions and ambient temperatures. NEC Section 430.52 provides guidelines for selecting the maximum overcurrent protection device for motor circuits. The maximum fuse size is typically limited to 250% of the motor's full load current for inverse time circuit breakers and 175% for time delay fuses. In this case, the nameplate specifies a maximum fuse size of 40 amps. This value is likely determined based on the motor's characteristics, the type of overcurrent protection device used, and the overall system design. Now let's address the question of wire size and circuit breaker selection. Assuming the unit is rated for 75 degrees Celsius terminations, the appropriate wire size can be determined using NEC Table 310.16, which provides ampacity ratings for conductors based on insulation type and temperature rating. For a 25 amp circuit, a 12 AWG copper conductor with THHN insulation is typically sufficient, as it has an ampacity of 25 amps at 75 degrees Celsius. However, it's crucial to verify the specific requirements of the equipment and local codes to ensure compliance. Regarding the circuit breaker, NEC Section 240.4d places restrictions on the overcurrent protection for certain small conductors. Specifically, 12 AWG copper conductors are generally limited to a 20 amp overcurrent protection device, unless specific exceptions apply. However, motor circuits are often granted exceptions to these limitations, as outlined in NEC Section 430.52. In this case, the motor's overcurrent protection device can be sized based on the motor's full load current and the type of device used. Given the nameplate ratings, a 30 amp or 40 amp circuit breaker may be acceptable, provided that it complies with NEC Section 430.52 and does not exceed the conductor's ampacity. However, it's essential to carefully consider the motor's characteristics and the specific requirements of the installation to ensure proper protection and compliance. In summary, determining motor nameplate values involves considering the motor's full load current, the characteristics of the connected equipment, and the applicable requirements of the National Electrical Code. The minimum supply circuit ampacity ensures that the branch circuit can handle the motor's load, while the minimum and maximum fuse sizes provide overcurrent protection without damaging the motor. Wire size and circuit breaker selection must comply with NEC regulations and the equipment specifications to ensure safety and reliability. Now let's delve into the specific calculations and considerations for determining these nameplate values. The first step is to identify the motor's full load current, which can be found in NEC Table 430.148 for single-phase AC motors or Table 430.150 for three-phase AC motors. These tables provide typical full load current values based on the motor's horsepower and voltage rating. For example, a 16 horsepower, 230 volt single-phase motor has a full load current of approximately 2.2 amps, according to Table 430.148. Once the full load current is known, the minimum supply circuit ampacity can be calculated by multiplying the full load current by 1.25 as required by NEC Section 430.22. This ensures that the branch circuit conductors have sufficient ampacity to handle the motor's continuous load. In our example, 2.2 amps times 1.25 equals 2.75 amps. However, as mentioned earlier, the nameplate value may be significantly higher if the AC condenser unit includes additional components. Next, The minimum and maximum fuse sizes must be determined based on the motor's full load current and the type of overcurrent protection device used. NEC Section 430.52 provides detailed guidelines for selecting the appropriate overcurrent protection device for motor circuits. For inverse time circuit breakers, the maximum overcurrent protection is typically limited to 250% of the motor's full load current. For time delay fuses, the maximum overcurrent protection is typically limited to 175% of the motor's full load current. In our example, if we were using an inverse time circuit breaker, the maximum fuse size would be 2.2 amps times 2.5, which equals 5.5 amps. However, since standard circuit breaker sizes are not available in such small increments, we would need to select the next highest standard size, which is typically 15 amps. Similarly, if we were using a time delay fuse, the maximum fuse size would be 2.2 amps times 1.75, which equals 3.85 amps. Again, we would need to select the next higher standard size, which is typically 5 amps. It's important to note that these are just examples, and the actual fuse sizes may vary depending on the specific characteristics of the motor and the type of overcurrent protection device used. The manufacturer's recommendation should always be followed when selecting fuses or circuit breakers for motor circuits. Regarding wire size, NEC Table 310.16 provides ampacity ratings for conductors based on insulation type and temperature rating. The wire size must be selected such that its ampacity is equal to or greater than the minimum supply circuit's ampacity calculated earlier. For example, if the minimum supply circuit ampacity is 25 amps, a 12 AWG copper conductor with THHN insulation would be suitable, as it has an ampacity of 25 amps at 75 degrees Celsius. However, it's essential to consider the dating factors outlined in NEC Section 310.15 if the conductors are installed in raceways or exposed to high ambient temperatures. Dating factors reduce the conductor's ampacity, and a larger wire size may be required to compensate. Finally, the circuit breaker or fuse selected must be compatible with the wire size and the equipment's requirements. NEC Section 240.4d places restrictions on the overcurrent protection for certain small conductors, as mentioned earlier. However, motor circuits are often granted exceptions to these limitations, as outlined in NEC Section 430.52. The circuit breaker or fuse must be sized to protect the conductors and equipment against overload and short circuits, while also allowing the motor to start and operate without nuisance tripping. In summary, determining motor nameplate values and selecting the appropriate wiring and overcurrent protection devices requires a thorough understanding of the National Electrical Code and the equipment specifications. The full load current, minimum supply circuit ampacity, fuse sizes, wire size, and circuit breaker or fuse selection must all be carefully considered to ensure safety, reliability, and compliance. Now let's discuss some additional considerations and best practices for working with motor nameplate ratings and branch circuit sizing. One important consideration is the motor's service factor, which is indicated on the nameplate. The service factor represents the amount of overload that the motor can handle for a limited time without overheating or being damaged. A motor with a service factor of 1.15, for example, can handle a 15% overload for short periods. However, it's important to note that operating a motor continuously at its service factor limit can reduce its lifespan. Another important consideration is the motor's insulation class, which is also indicated on the nameplate. The insulation class represents the maximum temperature that the motor's insulation can withstand without degrading. Common insulation classes include B, F, and H, with corresponding temperature ratings of 130 degrees Celsius, 155 degrees Celsius, and 180 degrees Celsius, respectively. It's essential to ensure that the motor's operating temperature does not exceed its insulation class rating to prevent premature failure. When selecting conductors for motor circuits, it's important to consider the voltage drop, which is the reduction in voltage that occurs along the length of the conductor due to its resistance. Excessive voltage drop can cause the motor to operate efficiently, overheat, and even fail. NEC Section 210.19a provides guidelines for limiting voltage drop in branch circuits, recommending that the maximum voltage drop should not exceed 3% for lighting, heating, and power loads, or 5% for feeder circuits. To minimize voltage drop, it's best to use larger conductors or shorter circuit lengths. Another best practice is to use properly sized and torqued connections when installing conductors and overcurrent protection devices. Loose or corroded connections can create resistance, leading to heat buildup, voltage drop, and even electrical fires. It's essential to follow the manufacturer's instructions and use the appropriate tools and techniques to ensure that all connections are tight and secure. When working with motor circuits, it's also important to consider the potential for harmonic currents, which are non-sinusoidal currents that can be generated by electronic devices such as variable frequency drives and electronic ballasts. Harmonic currents can cause overheating, voltage distortion, and equipment malfunction. To mitigate the effects of harmonic currents, it's best to use harmonic filters or reactors, which are designed to reduce the amplitude of harmonic currents and improve power quality. Finally, it's essential to follow all applicable safety procedures when working with electrical circuits. Always to energize the circuit before working on it, and use appropriate personal protective equipment such as gloves, safety glasses, and insulated tools. If you're not comfortable working with electrical circuits, it's best to hire a qualified electrician to do the work. In conclusion, understanding motor nameplate ratings and following best practices for branch circuit sizing is essential for ensuring the safety, reliability, and efficiency of electrical installations. By carefully considering the motor's characteristics, the applicable requirements of the National Electrical Code, and the potential hazards and challenges, you can create motor circuits that operate safely and effectively for many years to come. And always remember, when in doubt, consult with a qualified electrician or electrical engineer. They can provide expert guidance and ensure that your electrical installations comply with all applicable codes and standards. Furthermore, let's clarify some common misconceptions and address frequently asked questions related to motor nameplate ratings and branch circuit sizing. One common misconception is that the minimum supply circuit ampacity on the nameplate is the same as the motor's full load current. As we've discussed, the minimum supply circuit ampacity is typically higher than the full load current because it includes additional components and accounts for safety factors. Another misconception is that the wire size can be determined solely based on the minimum supply circuit ampacity. While the minimum supply circuit ampacity is an important factor, other considerations such as voltage drop, dirting factors, and conductor termination temperature ratings must also be taken into account. A frequently asked question is whether it's acceptable to use a circuit breaker or fuse that is larger than the wire's ampacity. In general, it's not acceptable to use an overcurrent protection device that is larger than the wire's ampacity, as this can lead to overheating and fire hazards. However, as we've discussed, motor circuits are often granted exceptions to this rule, provided that the overcurrent protection device complies with NEC Section 430.52 and does not exceed the equipment's requirements. Another frequently asked question is how to handle situations where the motor's nameplate ratings are not available or are incomplete. In such cases, it's best to consult with the motor manufacturer or a qualified electrician to obtain the necessary information. If the nameplate is completely missing, it may be necessary to estimate the motor's full load current based on its horsepower and voltage rating using NEC tables 430.148 or 430.150. However, this approach should be used with caution, as it may not accurately reflect the motor's actual characteristics. Another frequently asked question is how to handle situations where the motor's operating conditions are significantly different from those assumed during the design phase. For example, if the motor is operating in a high ambient temperature environment, it may be necessary to direct the conductors and overcurrent protection devices to prevent overheating. Similarly, if the motor is subject to frequent starts and stops, it may be necessary to use a larger overcurrent protection device to prevent nuisance tripping. In such cases, it's best to consult with a qualified electrician or electrical engineer to assess the specific operating conditions and make appropriate adjustments to the circuit design. Finally, it's important to stay up to date with the latest revisions of the National Electrical Code and other applicable standards. The electrical industry is constantly evolving, and new technologies and regulations are being introduced all the time. By staying informed and continuing to learn, you can ensure that your electrical installations are safe, efficient, and compliant with all applicable codes and standards. In summary, understanding motor nameplate ratings and branch circuit sizing requires careful attention to detail, a thorough knowledge of the National Electrical Code, and a commitment to ongoing learning and professional development. By addressing common misconceptions, answering frequently asked questions, and staying up to date with the latest industry trends, you can become a more knowledgeable and effective electrical professional.